Hi, Assalamualaikum and good morning everyone. My name is Nurul Adila and together with my group member Afham, Amir and Adila, we will be presenting about PN junction formation and depletion region. First, let me explain to you what a PN junction is. Okay, a PN junction is formed when P-type semiconductor material and N-type semiconductor material are joined together. The P-type material is created by doping semiconductor with trivalent impurities such as boron. This process creates holes, which act as the majority carrier series in the PN junction material. On the other side, the N material is formed by doping with pentavalent impurities such as phosphorus. This creates an excess of electrons, making electrons the majority charge carrier in the N-type material. When these two materials are brought together, they form a PN junction, which is a fundamental interface between P-type and N-type region. This junction is very important because it forms the basis of many electronic devices, especially diodes and transistors. Okay, and PN junction also play a significant role in our daily life. They allow for control current flow, signal modulation, energy conversion in billion of electronic devices used every day. Now let's move on formation of depletion region. Okay, when P-type and N-type material are joined, a spontaneous process occurs at the boundary between them. The first process is called diffusion. During diffusion, electrons from the N side migrate to the P side, while holes from the P side migrate to the N side. Next is recombination. Near the junction, the electron combine with the hole and neutralize the charge carrier, and this process continues. A region begins to form around the junction. This region is known as the depletion region. As shown in the diagram, before diffusion occurs, the P-type and N-type materials contain their respective majority carriers. However, after diffusion and recombination take place, a depletion region is formed at the interface between two materials. Okay, in conclusion, the PN junction is the meeting point of P-type and N-type semiconductors, while the depletion region is formed due to the movement and recombination of charge carrier near the junction. These concepts are fundamental to understand how semiconductor devices operate. Thank you. Next.
So for the depletion region, what happens when we join a P-type and N-type semiconductor together? So right at the junction, a thin layer forms called the depletion region. This region has no free electrons and no holes, and it is completely empty of mobile carriers. We can think of it as a barrier sitting between the two sides. So this happens because when two material meets, electrons from the N side cross over and fill in the holes on the P side. They cancel each other out, and this is what we call as recombination. After enough recombination occurs near the junction, that area is left with no free carriers at all. But something is still left behind. The atoms that lost their carriers become fixed ions. They carry a charge but cannot move. And on the P side, we get negative ions, and on the N side, we get positive ions locked in place in the crystal structure. So in short, carriers meet, recombine and disappear. What is left is a region of fixed charge with no free carriers. And so we will see in the next slide, these fixed ions are responsible for creating an internal electric field that controls the current flow through the junction. So next slide. So we left off with fixed ion sitting in the what we call the depletion region. So negative on the P side, positive on the N side. And these ions don't just sit there. They actually create a built-in electric field pointing from the N side towards the P side. Think of this field as a wall. It pushes electrons back on the N side and holds back to the P side, stopping any more carriers from crossing. This is how the depletion region maintains itself. Now, this electric field also produces a voltage across the junction. We call this as barrier potential, and it is basically an energy hill that carriers must climb over to get through. For example, for silicon, it's about 0.6 to 0.7 volts, and for germanium, around 0.2 to 0.3 volts. And this barrier is what controls the diode's behavior. With no bias, the field balance everything out. No current flows. With forward bias, we reduce the barrier and current flows through. With reverse bias, the barrier gets higher, the depletion regions will be more widened, and the current is blocked. So, in short, the fixed ions create a field, and the field that get created, the field creates a barrier, and that barrier is what gives the diode its ability to control the current direction. Thank you. Next slide.
Alright, next, let's start by looking at how PN junction behave under different electrical condition. So we beginning with forward bias. So forward bias occurs when we connect the P-type semiconductor to the positive terminal and the N-type semiconductor to the negative terminal of our battery. So a quick rule to remember this configuration is P goes to positive and N goes to negative. So this specific setup is what allow the diode to act as an open gateway for electricity. Okay, next slide. So right now we will see what happened internally when we turn this voltage on. So the external voltage directly opposes the diode built-in electric field. So as a result, the depletion region become narrow and shrink, and then lowering the internal barrier potential. So because of this barrier drop and the junction offer very little resistance. So this allow the majority charge carrier to easily cross the line. Holes float from the P region to the N region, while electrons stream from the N region to the P region. When they meet, they recombine near the junction. So a large current flow through the diode once your applied voltage beat the internal barrier, which is around 0.7 volt for silicon. So the current spike rapidly and the diode conduct electricity beautifully. So next slide. So right now we see about reverse bias. So for reverse bias, we can know the connection of the circuit is the P junction will go to the negative and the N type will go to positive. So this is the easiest way for us to remember how reverse bias look like. So next slide. Right, last, when we apply a reverse bias, the diode does a complete 180-degree in behavior. So instead of fighting the internal electric field, the external voltage actually strengthens it. So this caused the depletion region to widen significantly. So raising the internal barrier potential, the junction now act like a massive wall, offering high resistance. So instead of crossing over the barrier, the majority charge carrier are pulled away from the junction. So electron rush toward the positive and the hole towards the negative terminal. Because of this, the diode effectively blocks the current to flow. Alright, done.
Okay, thank you. So far, we have heard about the physical structure of the PN junction and how it behaves under forward and reverse bias. So, but how do we quantify that behavior? So, we have Shockley diode equation, which is, as you can see, I is equals to I naught times 2 exponent QV over NKT minus 1. So, as we know, when we apply the voltage in forward bias, the depletion region will become narrow, and as the barrier lowers, majority carries enough energy to diffuse across the junction. It means that when this equation tells us that current increases exponentially in forward bias. That means once you overcome that built-in potential around 0.7 for the silicon, even a tiny increase in voltage causes a huge jump in current. So for reverse bias, the negative one term dominates. So the current stays nearly constant at the tiny saturation current, which is I naught. So next. So this is the circuit demonstration. As you can see, for bulk on, the positive terminal will connect to P side, and the diode conducts, the current flows, and the bulb turns on. This matches what we just saw the exponential current flow. So in bulk off, the the positive terminal will connect to the diode at N side, and the diode will be in reverse bias. So the diode become insulator, the current doesn't flow, and the bulb turns off. So next, so these are the real life application that we are using the diodes. So first we have LED or light emitting diode. When the LED in forward bias, so it will emit the light, just like your phone's notification light, TV power indicators, and even large display screen all use LED. So second, we will have solar cells. These are large area photodiodes, operate in reverse bias or zero bias. Light generates electron hole pairs, producing the current is the same PN junction, just used in reverse. So the third one, we have rectifiers. As shown in earlier slides, rectifiers convert AC from your wall outlet into DC. Half wave, full wave, and bridge rectifiers all rely on diodes conducting in only one direction. And the last one, we have mobile phones. Inside your phone's charger, a bridge rectifier converts AC mains to DC. Then tiny diodes detect sensitive circuits from reverse voltage spikes. So that's all. As I can say, first, a diode is a one-way valve for current formed by joining P-type and N-type semiconductors. Second, its behavior is defined by the exponential Shockley diode equation, conducting strongly in forward bias and blocking in reverse bias. And the last one, this enable critical applications, just like rectification, lighting, power conversion, and protection in almost all electronic devices. So, thank you for your attention.
Okay, that brings us to the end of our presentation. We hope this presentation will help you understand how a PN junction is formed and how the depletion region develops. This process may seem simple, but they are the foundation of modern electronic devices. Thank you for your time and attention.